Hello, everybody. I am Mohamed Boutghatin, PhD student at the University of Lille in France. I will present to you the paper entitled Dynamic Thermoregulatory Photonic Crystal Fabric for Personal Thermal Management. According to the Agency of Ecological Transition in the European Union, the building sector consumes 45% of total energy consumption. More than 50% of this energy is attributed only to thermal regulation. Therefore, many efforts are being made to reduce this high consumption. In order to develop a new method of heating and cooling inside buildings, we need to understand how the human body exchanges the thermal energy with its environment. Globally, the human body exchanges its heat energy with the environment according to four mechanisms: conduction, convection, evaporation, and radiation. As we can see in the diagram at the right, radiation is responsible of more than 50% of the human body thermal loss. These radiations are an electromagnetic waves in the mid-infrared range. If we assimilate the human body to a black body, we use the Planck's law to calculate the infrared emissivity. We can see in this figure that the human body at the normal skin temperature 34 degrees emits thermal radiations between 3 and 15 micrometer. So, from this general context, our objective is to replace the common strategy of heating, cooling, building by a new approach. Our approach consists to propose a new generation of textiles able to modulate the thermal radiations emitted by the human body in order to maintain the thermal comfort. To achieve our objective, we propose to use the photonic crystal properties in the mid-infrared range of a microstructured polymer membrane. So here is the outline of the rest of this presentation. I will present the model and I will talk about the numerical method used. Then I will present the optical and thermal results. I will end the presentation with a conclusion. The fabric is composite of an ultra-thin metallic layer sandwiched between two polymer membranes with the same thickness. The three layers are dried with air holes following a triangular array. In this slide, I will explain how the fabric works. We consider that 34 degrees is the skin temperature of the thermal comfort feeling. We assume that the polymer is dynamic and temperature sensitive. When the skin temperature is below 34 degrees, practically we will feel cold, but the dynamic fabric will contract to reduce the transmission of the infrared radiations. So the fabric will heat our body to achieve again the thermal comfort. Now, if the skin temperature is above 34 degrees, we will feel hot. In this case, the fabric expands to maximize the transmission of the human body radiations in order to cool the body. To simulate the optical properties of the fabric in the mid-infrared range, we use the finite element method using commercial COMSOL software. We simulate an elementary unit cell of the fabric, and we applied the periodic boundaries condition in order to generate the complete structures. We applied the perfect matching layers to avoid any backscattering from the top and bottom boundaries. To simplify the study, we define the metallic layer as a perfect electric conductor. To simulate the dynamicity of the fabric, we define a scaling factor alpha from the three geometric parameters: the diameter of the air holes, the period of the array, and the thickness of the polymer membrane. This table summarizes 6 factors associated to a different set of geometric parameters. We calculate the reflection and transmission as a function of the scaling factor. Here I show you the results for 3 scaling factors. For the first factor, we can see that we have an occurrence of a transmission band around 3 micrometers. Now, if the fabric expands to achieve the other scaling factor, we can see that the transmission band shifts to the maximum of emissivity of the human body around 9.5 micrometers. So, for the small size, the fabric reflects more than 60% of the mid-infrared radiations. Therefore, the fabric realizes a heating functionality. But when the fabric expands, it reaches a cooling configuration because it becomes more transparent for human body radiations. To understand the origin of the transmission band, we present here the snapshot of the electric field. If we take the component EY, we can see here that the transmission of the electric field at 3 micrometers comes from the excitation of a symmetric stationary mode of this component. We can see that this mode is localized inside the polymer membrane and linked to the air medium. Now, to determine the thermal effect of the fabric, we use an analytical thermal model. This model is defined according to the thermal balance around the human body and the fabric. Then we calculate the ambient temperature set point to maintain the thermal comfort as a function of the scaling factor. We can see in this figure that the fabric is able to maintain the thermal comfort in a wide range of ambient temperature between 16.5 to 20 degrees. Also, due to its expansion and contraction, the fabric allows the heating and cooling functionality according to the room temperature. To conclude, we demonstrated theoretically by using a finite element method a dynamic thermoregulatory photonic crystal fabric. This fabric allows a human body thermoregulation by modulating the transmission of the human body radiations. Using an analytical model, we demonstrated that the fabric maintained the thermal comfort in a wide range of ambient temperature. Due to the air holes, the fabric is breathable, which is a crucial point for textile application. At the end, the authors would like to thank the Anteric Project Photonics. Thank you.